Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on February 20th, 2026, about 6 days ago. It presents a unified geometric framework proving that folding model weights, by clustering them together rather than deleting them, consistently outperforms traditional pruning methods across more than 1,000 checkpoints. The paper is titled Cut Less, Fold More, Model Compression Through the Lens of Projection Geometry. And as we'll see later, the empirical results across vision and language models are really impressive, suggesting a new default for calibration-free compression. To visualize those results, Figure 1 compares folding against magnitude pruning across 4 architectures, from ResNet 18 to Clip VitB32. In the scatter plots on the left of each panel, almost all the blue dots lie above the red diagonal line, meaning folding consistently achieves higher test accuracy. The bar charts on the right then quantify this gain. They show that the benefit of folding peaks at moderate to high compression ratios, where it often boosts accuracy by 10 to 20% compared to standard pruning. Moving to Figure 2, the authors check if this advantage holds up when we allow a tiny bit of retraining, specifically just updating the layer norm parameters. On the left, Panel A covers VitB32, while Panel B on the right shows Clip VitB32. Even with this lightweight adaptation, the scatter plots show folding consistently beating pruning, with points staying well above the diagonal. The box plots next to them drive this home. The performance gap actually grows as compression increases, reaching over 20% for the clip model. Well, having covered vision tasks, Table 1 shifts the focus to language modeling with Llama 60M. It reports perplexity scores on the C4 dataset across 18 different training setups, varying hyperparameters like weight decay and learning rate. The middle columns show that at 20% compression, folding consistently beats magnitude pruning, labeled MAG2. But the difference is most dramatic in the rightmost columns at 50% compression, where pruned models suffer huge spikes in perplexity, while folded models stay surprisingly stable. So, while Table 1 focused on calibration-free performance, Figure 3 asks whether folding still helps if we can fine-tune the model for a few epochs. The top row looks at ResNet 18 results, while the bottom row covers Clip VitB32. In the first column, the scatter plots compare folding against pruning after retraining. The blue dots lie predominantly above the diagonal, showing that folding retains its lead. The middle charts quantify this gap, although the advantage shrinks from the purple line at epoch 0 down to the red line at epoch 5, it stays positive. Finally, the panels on the right confirm that folded models recover lost accuracy much faster. Alright, while the previous results focused on accuracy, Table 7 examines the runtime costs for a compressed pre-act ResNet 18. The key takeaway is in the inference metrics on the right. Notice that latency and flops are effectively identical for both folded and pruned models. This happens because both methods produce the same final network topology. The only real difference appears in the comp time column, where folding takes about 9 seconds versus 2 for pruning. But since this is a one-time process, it is a negligible price for the performance gains. Okay, since the costs are similar, Figure 19 investigates the underlying geometry to explain the accuracy gap. It plots the worst-case L-infinity sharpness against the compression ratio. The top row displays results for folding, while the bottom row shows standard magnitude pruning. While sharpness generally rises with compression in both cases, the top panel show that folding tends to maintain flatter minima, especially for the clip model on the far right. Because flatter landscapes usually correlate with better generalization, this geometric stability explains why folded models stay more robust. So, having looked at sharpness, Figure 24 validates the paper's core theoretical claim regarding reconstruction error. The top grid of charts analyzes every layer in ResNet 18, while the bottom grid covers VitB32. In these plots, the blue line tracks the error for standard pruning, while the orange line represents a theoretical special fold, and the green line is the actual optimal folding. Crucially, the green and orange lines consistently stay below the blue one across all keep ratios, empirically confirming that folding is mathematically guaranteed to incur lower error. Wrapping up, 2 takeaways stand out. Model folding is a geometry-aware upgrade to pruning that consistently yields better accuracy, particularly at higher compression rates. By preserving the network's internal structure through clustering, it offers a robust, calibration-free method for efficient deployment without increasing inference costs. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.